So if you made it here, that means you've watched the eigenvalues and eigenvectors video and feel fairly comfortable with the concept of, what these things are and why we might be interested in these particular special vectors and these special values, and we can generate things like an eigenspace and basically, find these things which we call invariant, these vectors or spaces that are invariant under a transformation, which means, relatively speaking, they stay more or less the same, maybe just off by some scalar, right, getting stretched or shrunken, but, maintain primarily their very important properties, right, the properties that make up those vectors of that space. And this concept is pretty much the culmination of everything we've done in this class, and some big ideas regarding bases, eigenvalues, and eigenvectors. And so, to kind of start us off, I'm going to provide us a definition of what it means to be a diagonal matrix. And you might be able to kind of put it together in your head, but an n by n matrix A is diagonal. That's what we call diagonal. If it only contains entries or only contains non-zero entries along the main diagonal. That's also kind of a lie. Maybe we'll say that just in general, the idea is that if you have a square matrix, that you can have stuff on this diagonal and zero can be included in the diagonal. So this bit right here is a little bit of a lie in this definition. Maybe we'll modify it in a second. But the idea is that you basically have zero, you have zeros everywhere else, zeros above and below that kind of main diagonal there. But you could have numbers like 4, 2, 0, 1 here or something like that. And you get a nice n by n matrix. This is something that we call a diagonal matrix. So maybe I'll modify this definition a bit. So an n by n matrix is diagonal if and only, so if in every, we'll scratch this out. So if in every entry that isn't the main diagonal, there are only zeros in the matrix. Zeros in the matrix. Okay. And matrices, that we classify this way, diagonal matrices, are important, very similar to how triangular matrices have some nice properties. For instance, triangular matrices, we can calculate the determinant really, really quick. We can do the same thing here for a diagonal matrix, calculating the determinant, because a diagonal matrix is technically a triangular matrix as well. The determinant is still gotten by just multiplying the diagonals. But one other cool thing that we can do with diagonal matrices is we can calculate the exponent of a matrix very quickly. So, for example, if I give you the matrix D is equal to 5, 0, 0, 3, and I ask you to evaluate, if I ask you to evaluate D to the 5th power, say, something like that, normally just using matrix multiplication, we would just set up 5, 0, 0, 3 and multiply it by 5, 0, 0, 3. And when we do this row times column business, right, row times column, you're going to notice that in the first entry, we're going to get 5 times 5. I'm going to write that as 5 squared. In the second entry, row times column, we're just going to get 0. And then in the row times column that's in the third spot here, we're going to get 0 again. And then in the last space, row times column, we're going to get 3 squared as well. And if we were to continue this process due to the nature of where all the zeros are in a diagonal matrix, it turns out that D to the 5th is just as simple as the freshman dream of putting in exponents into your polynomials. We can do this for the matrix, and it just so happens for diagonal matrices, this is a really nice property. And so diagonal matrices are super simple. They're really easy to work with. You can calculate the determinant very easily. You can multiply the matrix again and again and again. And this is going to be kind of an interesting area of study for us because remember that a matrix can represent a transformation. And kind of one of the motivating ideas for studying diagonal matrices here is going to be, what if there's a way for us to write a transformation like a diagonal matrix? Okay, because if we have a diagonal matrix and it represents a rotation or something, and I say, I want you to take that matrix and I want you to do the same transformation 3 times. I want you to rotate it however many degrees you're going 3 times. It's a lot easier to figure out, okay, well, if I want to do, that matrix 3 times and then multiply it by some input vector x, it's very easy to be like, oh, well, this matrix is just going to be 5 cubed, 0, 0, 3 cubed. And then I'm just going to pop in my x vector, and then I can tell you exactly, what this vector x evaluates to after I've applied the transformation d to it 3 separate times. So this is going to be it's just a really, really nice shortcut for us to work with. So the big question is, where are we going with this? The big idea in this section is it turns out that if a matrix A has n distinct eigenvalues, then we can what we call diagonalize. We can diagonalize the matrix such that A is equal to P D P inverse. I'm going to explain what all of these things are here. Okay, so P is a matrix that consists whose columns, the columns of this matrix, the columns consist of the eigenvectors of A. So another thing to kind of point out here is that if A is an n by n matrix, but we don't have n eigenvectors, right? Let's say we have, if we have less than n eigenvectors, then A is not diagonalizable. It's not diagonalizable. Okay. And I know that none of this kind of probably makes sense. I think you're going to just have to kind of keep rolling with the punches for the next couple minutes until, things start to kind of make a little bit of sense here. So the matrix D consists of, D stands for diagonal. It is a diagonal matrix, so everything that is not along this main diagonal is just 0. But the diagonals consist, it turns out, of the eigenvalues of A. Okay? And then everywhere else is 0. 0, 0, 0, 0, 0, 0, 0, 0 everywhere. 0 everywhere else. So what's P inverse? Well, P inverse, that's literally just the inverse of our matrix P here. Now, usually, at this point, people are like, okay, first and foremost, where the hell did this come from? Can you, justify this for me? Okay, sure. So, let's pretend just for a second, right? An equivalent form of this statement would be to multiply both sides by P, right? Multiply both sides by P on the right. The P inverse and P will cancel. So, showing that these are the same is basically showing that this is also true. So let's take a look at the left side. Okay, let me prove to you that I'm not just I am making it all up as I go, but not to the extent where it doesn't work. So this would be like saying we have A times the matrix P, and the matrix P consists of our eigenvectors v1, I'm going to call them v2, right, vn. Okay, so that's what the left-hand side is. And, A is a matrix, so if you want to think about it, you could say, that we kind of apply the matrix A into all of these, and we get like AV1, AV2, AVN on the left side. And then on the right-hand side here, what's going on the right side? Well, on the right side, we have P times D. Okay, so P consists of V1, V2, V sub n. But D is this diagonal matrix that I've claimed consists of the eigenvalues for the matrix A, right? So consists of these eigenvalues. And if we do row times column, right? If I do row times column, and I do it for all of these, then on the right-hand side here, what am I going to get? I'm going to get, well, for the first one, row times column. Remember, I have, this is a 1 by n, and then this thing over here is n by n. So what am I going to get out? I'm getting a 1 by n matrix, so 1 row, n columns. And I'm going to get out, in my first place, I'm going to get lambda 1 v1. In the second one, I'm going to get lambda 2 v2, and I'm going to get lambda n v sub n. And so as long as these lambda 1s, as long as I've set them up in such a way that this eigenvalue is associated with this eigenvector. So just to pause and clarify really quick, you have to set this up in such a way where these eigenvalues here match the order of the eigenvectors that you put over here. As long as these match, these two things are equivalent, because by definition, if we have these eigenvalues, then by definition, this statement here is true, right? That A v1 should be equal to lambda 1 v1. And this is the reason why, this can't be the eigenvalue for the second one, because that wouldn't make any sense, and then this statement wouldn't be true. So we got to make sure that we line some stuff up. Okay, so that's a lot of information, and so what's summarily, what should we take from this? So the idea is that, so one such way that we could be guaranteed that A is diagonalizable is if A has n distinct eigenvalues, that will do the trick. Another criteria that would also work is if we have n distinct eigenvectors. And you might be wondering, well, what, those don't those mean the same thing? Not exactly, right? Because if we have n distinct eigenvalues, that means we are going to be guaranteed n eigenvectors, because each little lambda has to be associated with some vector v by definition of being an eigenvalue. Right, so the first one guarantees that we have n eigenvectors, so we're good. The second one, we don't necessarily have to have n distinct eigenvalues, right? We've done problems in the last video where one eigenvalue has two distinct eigenvectors, v1 and v2, and that was when our eigenspace was of dimension 2, right, and it spanned a plane or something like that in one of our spaces. So when we're creating this, when we're taking a look at the fact that A is equal to P times D times P inverse, what this is really saying is that when we set this up, this is a true statement. I kind of just briefly above did some light theory just to kind of loosely, but showing you that it is indeed equivalent. When I set this up and I pick my matrix P, right? If I set up and I put my first eigenvector and my second eigenvector and then my nth eigenvector here, and I set up my matrix D now, if one eigenvalue has a multiplicity of 2, remember that if this thing has 2 distinct eigenvalue or eigenvectors, that means it has a multiplicity of 2. If this lambda 1 works for both of these eigenvectors, then what I'm going to end up doing is, lambda 1 essentially goes there, and then, I'll just call it lambda 3 and then lambda n. So this will always ensure that, that we have n that we have n eigenvalues going along in the diagonal here, but they don't necessarily have to be distinct. If you are distinct, you immediately get it for free, but if they're not distinct, then you have to check and make sure that you're at least getting n eigenvectors so you can do this process. Okay, so what's the big deal? What's the whole shebang? I think before I answer that question, I'm just going to show you like, hey, we can do this thing, and then I'm going to introduce you to a little bit more theory. Okay, so let's try and diagonalize this like a matrix. So for example, all right. So example, so diagonalize the matrix A is equal to 1, 3, 3, negative 3, negative 5, negative 3, 3, 3, 1, if possible. Okay, if possible. All right, and I've already told us how to do this, right? So we need to check that one of these two criterias holds, right? We need to check this thing, but as long as one of those two criterias holds, then I've already told you how you find P. I already told you how to find D, and P inverse is just the inverse of the matrix P. And since these are n distinct eigenvectors, means they're all linearly independent. That guarantees us, since this is also an n by n matrix with linearly independent columns, that guarantees us that P inverse actually exists and we can do this thing. So the very first thing that we're going to do is find the eigenvalues of this matrix, right? So step one is find the eigenvalues, okay? We want to find the eigenvalues of A. Now, since this was an exercise from the last video, this is something that we've covered quite extensively in the last video, I'm going to skip it and just give you that. I'll give you the characteristic equation and we'll make some inferences from there. So the characteristic equation ends up being 0 is equal to negative lambda minus 1 times lambda plus 2 squared. Okay, and so what does this mean? This implies that we have eigenvalues that our first one is lambda equals 1 with, a multiplicity of 1, and the second one implies that our second lambda is going to, or our second eigenvalue is going to be negative 2, but it has a multiplicity of 2. And so here, how many eigenvectors do we need to actually perform diagonalization? Well, because this matrix here is a 3 by 3 matrix, we're going to need 3 eigenvectors. That's the idea. And so we already know that we're guaranteed to get at least 1 with this one. So the one that we really want to check to make sure that this works is this second eigenvector for negative 2. Now, we're going to need all the eigenvectors, but I'm going to start with the second one because if the second one we only get 1 eigenvector, then we're done, and this thing is not diagonalizable. We can't do it. It won't work. Okay, and the reason is just the theory of how these lambdas are supposed to line up with all these vectors and how the matrix multiplication works. Okay, so let's solve for one of these. Okay, so to solve for the eigenvectors of this matrix here, we would set up 1 minus lambda, or I guess in this case we have our eigenvalue already is minus 2. So 1 minus negative 2, which is plus 2. We have 3, 3, then negative 3, then we have negative 5 plus 2, negative 3, 3, 3, and then 1 plus 2. So we get a matrix 3, 3, 3, negative 3, negative 3, negative 3. Wow, 3, 3, 3. This is so nice. And remember that what we're doing right now is we're basically going to augment this, set this equal to 0, right? This is now an augmented matrix problem because we're essentially, right, we've moved everything. We did ax minus lambda x is now equal to the 0 vector, and we're solving this. And, it takes no time to see that this thing's just going to essentially reduce to 1, 1, 1, 0, and the rest of these rows are just all the multiples of the first one. So we get to here in RREF, and this implies, right, what does this imply? This implies that x1 is equal to negative x2 minus x3, which implies that our eigenvector here is of the form negative x2 minus x3, x2 and x3. And so that's going to give us that our eigenvector here can be split into two distinct eigenvectors, where one of them is going to be, with an x2 here, we're going to have a minus 1, 1, 0. And then we're going to tack on our x3, and we're going to have a minus 1, 0, and positive 1. So we have two distinct eigenvectors for this one, so we're going to be good to go. I guess we should do this one, but because this video is a little less about actually finding the eigenvectors and more about this thing about diagonalization, I have this one prepared. And it is for lambda, I'll just call it our eigenvector, and I guess I should call this one the second one. That this eigenvector here is going to be 1, negative 1, and 1, like so. So we have three distinct eigenvectors. They're all linearly independent, and because we have this, I claim from about 10 minutes ago worth of work. So this implies that our P matrix is going to consist of, so I'm going to put the first eigenvector associated with the first eigenvalue as 1, negative 1, 1. Then I'm going to put the second and the third one, negative 1, 1, 0, and negative 1, 0, 1. That's our P. This implies also that D is this diagonal matrix, which is 1, negative 2, and negative 2, since negative 2 makes an appearance twice. And the only thing that we have left to calculate is P inverse. And again, I have this prepared just because we've done inverse calculations in the past, but let me write down the inverse of P really quick. So the inverse of P, so P inverse here ends up being this really nice matrix: 1, 1, 1, 1, 2, 1, negative 1, negative 1, 0. And so I claim, right, we've done all this work, and we hope that I haven't been leading you astray. I claim that the matrix A, which is 1, 3, 3, negative 3, negative 5, negative 3, 3, 3, 1, hopefully equals my P matrix 1, negative 1, negative 1, which consists of my eigenvectors. And then my diagonal matrix 1, 0, 0, 0, negative 2, 0, 0, 0, negative 2. And then my inverse, which is 1, 1, 1, 1, 2, 1, negative 1, negative 1, 0. Now you should be very skeptical, and this one I will actually do for you. We're going to actually do the matrix multiplication just this one time to show you that it actually works. So I'm going to do these first two first. And so if I do, let's see, row times column, I believe for my first entry with the first row and the first column, I just get a 1. First row, second column, I should get a positive 2. And then first row, third column, I also get a positive 2. Second row, first column, I believe I get just a negative 1. Then I just get a negative 2, and then I get 0. And then for the third row, first column, we should get a positive 1, get a 0, and then get another 0. If I haven't made any mistakes, one of the biggest sweaty parts about doing this. And then now I'm going to multiply the last two, and let's see what we get. So if I do the first row times the first column, and we'll just kind of go from there. First row, first column, I get 1 plus 2 is 3 minus 2 is back to 1. Okay. First row, second column is going to be 1 plus 4 is 5 minus 2 is 3. And then, let's see, for the third one, we get 1 plus 2 is 3 plus 0 is also 3. So things are looking promising. We'll do second row, first column. So we got -1, -3, and then 0, so -3. We're going to get, for this row, this column, -1, -4 is going to be -5, and then 0, so -5. And then in the next one, we get -1, -2, so that's going to be -3. And then for the last one, this one's easy because there's a bunch of zeros. So last row, first column, we just get 1, right? So since this just has a bunch of zeros, we're actually just going to get the first entry in all of these. So 1, 0, 0 is what I'm getting, and that doesn't match what we have. So did I do some math operation wrong earlier? Let's go back. So to get this last row here, we do the third row and then this column. So I believe I'm getting 1, I'm getting 0, and I'm getting, a -2 in this last spot. I'm getting a -2 because I can't do math. So this is a -2 here. There we go. And this is stuff that you should all do. You should be like, hey, Dylan told us this thing. This is a theorem. It should work. Yeah, I'm here telling myself that I screwed up. Okay, so now let's see if we checked it. So now if we do this row times, all right, this looks a little better. So if we do that, we're going to get 1 minus -2, so plus, so it's a 3. Then I'll get 1, 0 plus 2 is 3. And then for the last one, now I get a 1. Okay, cool. So it works. Phew, sweating. All right. So again, all right. So our big takeaway at this point, now that we saw that this, we actually do get this matrix, the big takeaway is that I can do this process, which is called diagonalizing a matrix. And it turns out that if I do this, one really nice property of doing this from maybe just an algebraic standpoint is if I have you to calculate like a to the 5th power, right? Now you might be like, well, we could do it. I'm like, yeah, you could do it. This matrix looks terrible, right? If I asked you to do the 5th power of this matrix here, you might cry or drop out of the class, which would totally be warranted. But if I write it in this diagonal form and I say, hey, I can rewrite this matrix A and kind of like to think about it like the factored form of a matrix, if you will. If I can write it in this form, then what does A to the 5th even look like? Well, I would take A, right, and I would multiply it by itself 5 times. I have PD, P inverse, dot, dot, dot. PD, P inverse. But what's going to happen? What do you notice that happens? Well, every time on the inside here, we're going to get a P inverse times a P and a P inverse times a P and a P inverse times a P. All of those things are going to cancel out. And it actually turns out that we would be left with P. Then I'd have D times D times D times D times D. So I'd have D to the 5th power times P inverse. And what did we say earlier? What's like the power of diagonal matrices? Well, diagonal matrices here would just be P, and since our diagonal matrix here consists of is this guy right here, we're basically just doing 1 to the 5th, -2 to the 5th, and -2 to the 5th here with zeros everywhere else because that's our diagonal matrix D. And then P inverse, right? It has this nice property that because it's diagonal in nature, doing exponents is pretty easy. And this is not too bad, right? We take P, right? I get 1, 0, 0, 0, -2 to the 5th power is -32, 0, 0, 0, -32. And you're like, but Dylan, I still have to do matrix multiplication. I got to multiply P and then I got to do P inverse. I'm like, yeah. Okay. Yes. You still have to do some multiplication, but at least you don't have to multiply this guy 5 times. That'd be terrible, right? You'd be here for hours. So this is like a more optimal way of doing the same transformation over and over and over again. Now, that can kind of seem like a bunch of BS if you're, in this class and you're just like, all right, cool, I guess we can do this. But you said we can diagonalize A. What does that even mean? The actual kind of power of what's going on here is something that is like mildly beyond the scope of this class, but I'm going to try to enlighten you all anyways as to why on earth I just decided to bring this theorem that we could, if A has n distinct eigenvectors or it has n distinct eigenvalues, then we're good to go. And we can write this matrix in this form. Why did I choose to bring this up? Well, remember earlier in the past videos, we were talking about these things called bases, right? And one of the most motivations for learning about eigenvectors was that eigenvectors are these special vectors that don't really undergo much change underneath a transformation, right? They might shrink a little bit. Maybe they would swap direction because there's a negative or something, but at most they're just off by a scalar. And if you have more than one eigenvector for a particular eigenvalue, then it forms what we call an eigenbasis, right? And so on and so forth. And so that entire plane basically doesn't change. And in that particular video, I commented that, when we're talking about bases, why would we want to use a different basis than the standard basis? And one of the justifying things that I brought up was, if you're working with a particular topic where, like in crystallography, I believe was the example I gave, where all of your crystals are tilted a little bit, right? It makes more sense to use basis vectors that are tilted in this particular way when working, with crystallography than it does to use the OG basis vectors that are just kind of straight up and down. This is much more convenient based on the math that we're working with. Well, it turns out that if you have enough of them, namely you have n of them, these eigenvectors can be used to create what's called an eigenbasis. And an eigenbasis is exactly what it sounds like. An eigenbasis is a basis that consists of eigenvectors. And that is super useful in mathematics for the kind of very loose reason that I've given here with this crystallography idea. Now, how does this relate to what we're doing? This matrix right here, if A is diagonalizable, consists of n distinct eigenvectors, which means that the column, that implies that the columns of P are an eigenbasis for our space, right? And here is like the big power behind what it is that we're doing. Now, I'm going to do this without rigorous proof. If you want rigorous proof, we can talk about it in office hours, or I can send you links to what to read. But the idea is that, remember A is like a transformation, right? A is a transformation. It takes us from some space to some space, or A is representative of a transformation, I should say, right? So there's some transformation going from some space to some other space, and A is the machine that gets us there, that represents the workings of this transformation. Now imagine that I have to do this transformation a bazillion thousand times in a computer, right? So, I have to, let's say it's a rotation, or I'm taking a picture and I'm stretching it, or I'm blurring parts of it, or whatever, right? So this matrix is this big box of numbers, and every single slot is probably filled out with numbers. And I have to do this, a bazillion thousand trillion times for every single vector that's represents a particular, pixel of color on my screen. That can get very tedious to do for a computer program. So what you can do instead is I can take the fact that if it turns out that A is diagonalizable, and I can write it like this, then I can multiply both sides by P here on the right side, and I can multiply both sides by P inverse on the left side. And what happens is that P inverse and P cancel, and this P inverse and P cancel here. And what happens on the left side is we just said we have P inverse times A times P, and that equals D. Okay, remember that D is a diagonal matrix, right? A diagonal matrix. And what you can think of what's happening here, again, this is without proof. It's just to kind of give you a why would I care about this moment in your life. You can think about what's happening here is that P, which consists of these very interesting eigenvectors that form an eigenbasis for our space, and P inverse here are turning my matrix A into this diagonal matrix D. That's what's kind of going on. And so this matrix D here, this matrix is the transformation. It's the same, I'll say it's the same transformation that was represented by A. That was represented by A. And now here comes the caveat, ... with respect to the eigenbasis. Okay? And so let's take a step back what that means. That means that if I take a space, right, and A is the transformation that it represents a transformation that I'd be doing on this space to do some stuff, right? Maybe I have a picture here and I want to do stuff to it. But then I decide, hey, look, if I decide to work not with that coordinate system, but I want to use, say, that vector and this vector, which I've decided are eigenvectors, I want to use those as my basis vectors for this space to talk about the coordinates of points in this picture. And so I recalibrate everything so that all of my points in this picture are the coordinates that I'm given are not with reference to the standard basis, but they're with reference to the eigenbasis. Then that means that I can now just consider my transformation as a simple diagonal matrix. And then remember all of those thousands, bazillions of transformations that I might have to do again and again and again and again and again. Well, now I can do them again, no problem. I could do d squared, I could do d cubed, I could do d to the 100th power. No problem. Take about 5 seconds for my computer to do it. No problem. Okay, so this is like one of the main reasons why we care about diagonalizing things. If you want, you can equate it to why do we factor? Well, we factor things because it's useful. This is a thing that we can do to a matrix, right? If this matrix P consists of eigenvectors, D consists of corresponding eigenvalues. The inverse of P is something you calculate. And if you want to read a little bit more about the change of basis, there's a section, it's 4.6. I might have a video about it later, but at the very least, you can just kind of read about it to kind of get some intuition. And the idea is that if I do this, not only can I now, calculate A to the 10th power really easily because this side just ends up being, multiplied by itself 10 times. That 10 gets absorbed essentially into the D matrix. But I can also do things like now I can consider the transformation with respect to a different basis, and it's a much nicer, simple looking matrix to work with. So much more simple to work with, and it consists of the eigenvalues of the matrix A, which is also just a trip to kind of think about. Okay, so I think this video is long enough. We've talked about a lot of stuff and most of it probably honestly doesn't make sense because the first time I ever learned this, the first viewing, I just thought why are we doing this? Where does this formula come from, et cetera, et cetera. So take a moment to scroll back, kind of especially in the theory part, right? Like I kind of just pulled out of thin air that we can diagonalize stuff, that it forms. To diagonalize a matrix, it takes on this form. If you want to do a little bit of additional reading, you can read about similar matrices. So similar matrices in the text, or you can Google it. A similar matrix is any matrix that you can write it of this particular form. So if you can find some matrices that this works, then you would say the matrix B is similar to the matrix C. So, in that regard, if you caught what I just said, that means that the matrix A here, A is similar, so we call similar to the matrix D. And similar matrices contain a lot of properties, such as like the determinant is the same, the dimension is the same, the trace, which is something we don't know anything about yet, but the trace is the same. It contains a lot of properties that are all the exact same, as the same characteristic equation, as all this good stuff. And not only that, it embodies the information encoded in A, right? It is the same transformation that A was, except it's the same transformation with respect to this eigenbasis thing that I talked about earlier. So I think that's going to do it. What should you walk away from this section knowing how to do? You should know how to multiply diagonal matrices in about 2 seconds. If you're given the diagonalization of a matrix, then you should be able to calculate this matrix to a power in about, well, maybe not 5 seconds, because you actually still have to do the math on the right hand side, but you should know a shortcut now for doing it. And you should also know how to determine whether or not a matrix is diagonalizable. So these are criteria. You can have one or the other or both at the same time. But the second one is like the most important one. And then the last thing, of course, you should be able to do is actually diagonalize a matrix, right? To actually go about finding the eigenvalues, find the eigenvectors, put them in the correct corresponding order, figure out the inverse of P, and then set up your set up your final matrix as the actual diagonal form, right? To set it up in this particular way. I'm going to stop talking now. You all have fun with this section, and of course, email me, shoot me emails, post in the discussion, all that good stuff. If you have any questions, and read the textbook. If you're having trouble with this section, also bust out the second textbook that's also in Canvas to get maybe like a little bit of a different take on the process of diagonalization and see more worked examples. That's going to do it. We only have one more video after this, and then we're pretty much done with the class. So congratulations, but don't celebrate yet, because you got to go get to it right now.